Here we have an interesting example to see if we use a fan to reduce the temperature. Usually we use fan to reduce temperature inside our houses, inside the room and so on. But we will see in this example which it is not enough if we just put a fan inside the house. The changes in the temperature inside the house by using a fan depends on some other factors as well. We'll see what will be those factors. We have a room like this, then we put a fan inside the house. We run the fan and we know how much is the initial temperature of the house. We know how much is the power which is required by the fan, or electrical power of the fan required by the fan, and also we know how much is the heat transfer from the room as our system, the air inside the system, we get that as our control volume, or our system. Then the heat transfer from this system to surrounding, which is outside of this room. Also, we know how much is that, or rate of heat transfer, we know how much is that. Okay, let's see if by this much of heat transfer and this much of electrical consumption for this fan, we can cool down this room or not. The initial temperature of the room is 25 degrees Celsius. We put this large fan. It consumes 200 watt of electricity when it is running on. And we know how much is the rate of heat transfer. Heat transfer, as you know, it is due to the temperature difference between two different objects, I can say. Here you can, or two different bodies. Here we have the air inside the house, and then boundary inside the room, and then boundary, and then surrounding. So the equation for heat transfer for this room is like this: Q dot, or rate of heat transfer, is equal to UA Ti minus TO. Ti is the temperature of the inside the room or indoor. TO is the temperature of the outdoor or out of our system. A is the surface area of the walls and also the ceiling of this house, which are the surfaces for heat transfer. And also U, which is a parameter, we call that overall heat transfer coefficient. You may know about that from your heat transfer subject, that this is a characteristic of the materials which we have here, and it depends on also other characteristic of the the heat transfer type and so on. But here we have the equation. So the rate of heat transfer will be like it depends on the temperature difference between these two media, inside and indoor and outdoor of the room, and also surface area, and U, which we have both of them. A is 30 meter squared, and it is for a surface area of the room, and TITO are the indoor and outdoor air temperatures. What we should do is to determine the indoor air temperature when a steady operating conditions established. In other words, the room temperature, or the temperature of the air inside the room, is equal to the temperature of outside the room. So initial temperature is 25 degrees Celsius. Then we put this fan inside the house. It will start to working, to blowing the air inside the room. Then temperature of the room starts to change because of the movement of the air and because of this heat transfer. But as you notice here, if we just simply see the how is the energy transfer for this system is the air inside the house. The electric power come to the system, which we call that W dot electric in, and thermal energy, which will go out from the system by heat transfer, Q dot. Then we should, let's see what are the assumptions. One, heat transfer through the floor is negligible because it is not mentioned about that anything. And also we can imagine it is negligible because usually heat transfer from the walls is much higher than the floor of the house. And there are no other energy interaction involved. We have only these two types of energy work. Electric will come to the system, and thermal energy will go out from the system. This is our assumption. Then the electricity consumed by the fan is energy input for the room, and thus the room gives energy at the rate of 200 watts. As a result, the room air temperature tends to rise because this electricity come to the system, and this is like a resistance because it's come to the system. It causes the fan to run, and because of the resistance in the wires, it temperature will increase. This electric power. When energy come to the system, this work it will convert it to the uh, temperature inside the room because of the resistance in the wire, in the motor of the fan. As a result, the room air temperature tends to rise. But as the room air temperature rises, the rate of heat loss from the room increases until the rate of heat loss equals to the electric power consumption. As you notice here, as much as the temperature difference between indoor and outdoor of the or between the inside the system and outside of the system is higher, Ti minus To higher, Q dot is also higher. I mean more energy is transferred from the room to the outdoor. So when we put this fan, it increases the temperature. Increase in the temperature inside the room will increase the temperature difference between inside and outside of the system. It means this rate, the Q dot out will also increase. More energy comes to the system, more energy goes out of the system. But initially they are not equal. W dot is not equal to Q dot, so it will be different. But after some while, they will reach a steady condition, which this temperature difference will be constant because as much as energy comes to the system, energy will go out of the system. So after a while, they will reach a stable condition or a state in the system. Then, but as the room air temperature rises, the rate of heat loss from the room increases until the rate of heat loss equals to the electric power consumption. Q dot out equal to W dot. At that point, the temperature of the room air and thus the energy content of the room remain constant. And the conservation of energy for the room becomes this equation. You know about this equation, it is conservation of energy for the room. E dot in minus E dot out, or rate of the net energy transfer. These terms, two parameters. The difference between them will be rate of net energy transfer for the system. And this term, dE system divided by dt, is rate of change in energies of the system, which because we imagine they reach a steady state, then it means no change with time in the system. Remain constant everything. Then this term is 0. In other words, E dot in is equal to E dot out. W dot electric which come to the system is E dot in. Q dot out, or the thermal energy which go out of the system, is Q dot out. And we know how much is Q dot out. We have an equation for that. And also W dot electric, or electric power, also we know that it's 200 watts. We know how much is U, it was mentioned, how much is the A, it was mentioned or given by the question instruction. And also we know how much is TO, or temperature of the outdoor. Okay, with this situation, we are going to see how much will be the TI. By rearrangement, we can calculate TI for this system, or for the air, which is the temperature of the indoor after, this process. It will be 26.1 degrees Celsius. You can see here an interesting characteristic, or interesting result for this example. You can see here we put a fan inside the room to reduce the temperature of the air inside the room, but finally temperature is increased 1 degree Celsius. The temperature of the room after a while, after reaching a steady state, will be 26.1 degrees Celsius. It is increased by 1.1 degrees Celsius. Why? Because we use a large fan for this room. Why? Because we didn't use good insulation materials to reduce this Q dot out. If we can reduce this, or the main problem is the fan actually. The fan should be selected according to the size of the room. So you should note that this fan, which is power consumption, or simply when you are going to buy a fan, its power consumption is mentioned. 200 watt fan heats the room just like a 200 watt resistance heater. Instead of a cooling device, it is a heating device for this room. Why? Because the fan, the motor of that, converts part of the electric energy. It draws to mechanical energy in the form of rotating shaft, while the remaining part is dissipated as heat to the room air because of the motor inefficiency. Not all of the electrical power which come to the motor of the fan be converted to the mechanical energy. Some part of that will be thermal energy due to the friction in the motor components, and even because of the resistance in the wires, which are connecting lines from the source, electricity source to the motor of the fan. In other words, we don't have any equipment with 100 efficiency. The best case for large ones is 97%. And also the shaft, and part of this mechanical energy of the shaft is converted to kinetic energy of air through the blade. Fan blades are turning, and they push the molecules of the air, then their mechanical or kinetic energy will increase, which is then converted to thermal energy as air molecules slow down because of the friction. So we have also another source of increase in the temperature of the room. Movement of the molecules and friction between the molecules, and also molecules and the blade of the fan, will produce some kind of temperature or thermal energy inside the room. At the end, the entire electric energy drawn by the fan motor is converted to thermal energy of air, which manifests itself as a rise in temperature. So you can see here, we cannot always use a fan to reduce temperature inside the room. We should select the fan according to its power consumption and heat transfer capacity of the room. Here is another example of how we can use the concept of energy or energy balance to see how much is the annual lighting cost, for example, of a classroom. These can be any places, home, office, anywhere, and or which we are going to use the lighting source. So let's see how we can calculate the cost for lighting of a imaginary classroom. The lighting needs of a classroom are met by 30 fluorescent lamps. So the source for the light is 30 fluorescent lamps, each consuming 80 watt. So the electrical power which is required for each one of these fluorescent lamps is 80 watts. The light in the classroom kept kept on for 12 hours a day and 250 days a year. So this is the duration which these lights or these lamps should be on. For a unit electricity cost of 11 cents per kilowatt hour, determine annual energy cost of lighting for this classroom. Also discuss the effect of lighting on the heating and air conditioning requirements of the room or the class. Okay, so as you may guess from the question as well, we are going to calculate the annual cost by this information, which is for the uh, these 30 lamps. First of all, the you know that we should calculate the uh, lighting power. Lighting power means we have 30 lamps, and we know also how much is the power consumed for each lamp. So power consumed for each lamp multiplied by number of lamps will be the total value of the required power for lighting this class, which is 2400 watt or 2.4 kilowatt. This is the total or net power for the lighting the class. Okay, but we will also check, because this is a kilowatt and the lighting power which is required. Let's see how, according to the duration, how much will be the uh, required power. The operating hours also, we have that for 250 days per year we are using this lighting. For example, in the summer, in some countries, or also here in Malaysia, the some days, weekend, and also in summer, the universities and schools are closed, so we don't need the lighting source. So we have 250 days per year, and each day we will use these 30 lamps for 12 hours per each day. So 12 hours per each day times 250 days per year will give us this information, which is the the hours per year which these lamps should be on. Then the amount and cost of electricity used per year. We need to find the lighting energy. We have the power, lighting power times operating power will be the lighting energy, which is the lighting power is 2.4 kilowatt. For we should multiply that to 3000, which we have calculated in previous step, and it is the duration in per year which this power is required. We need 2.4 kilowatt times 3000 hour per year. The result is we need 7200 kilowatt hour energy per year to uh, lighting this class. So this is the required energy. Then lighting cost, also we have that it is 1 cent per kilowatt hour. How much is the lighting energy required? 7200. Simply, if we just multiply this 7000 kilowatt per hour per year, multiply by 0.11 dollar cents per each kilowatt hour, will be the amount or cost of lighting of this class per year. $792 per year will be the cost for lighting this class, this imaginary class. So you can see how we can use the concept of energy and for a system, which here is the class, to calculate the uh, energy which is required for that class for any specific purpose. Here is light. So, and in terms of the thermal energy, light is absorbed by the surfaces, it strikes and is converted to thermal energy. So temperature inside the class will increase because of the radiation and conversion of the electrical energy to the light, and light, as you know, is a source for the thermal energy by radiation. Disregarding the light that escapes through the windows, the entire 2.4 kilowatt of electric power consumed by the lamps eventually become part of thermal energy of the class. So the thermal energy of the class also will increase this much, 2.4 kilowatt. Therefore, the lighting system in this room reduces the heating requirement by 2.4 kilowatts, but it increases the air conditioning load by 2.4 kilowatts. You can see here how these light sources, this light source or these lamps can be effective also on the temperature inside the room. If we imagine there isn't any, there isn't any loss of this radiation or this light energy from the windows, and if we imagine all of the radiation energy by the lamp is absorbed by you know the the glass, it means 2.4 kilowatt will be increased in the uh, energy of the system or temperature or thermal energy of the system. And in cold areas, it is helpful. It reduces the cost for increase the temperature or heating the glass. And in the hot areas, it will add extra requirement for air conditioning, which is equal to 2.4 kilowatt as. And you can see here how the lighting also can be effective on the this air conditioning or heating source, which it is also it should be also included in our calculation to see how much is this light source totally effective on the cost for that classroom. I mean, if we need more air conditioning, if we need more heating source, it means it costs also for us. So the total cost will be higher than this $792 per year. It will be higher due to the change in the thermal energy of the system. Okay, the other important things about the thermodynamic side of the system is their efficiency. Efficiency or performance of any system means how much is the output or desired output of that system compared to the required or provided input for that system. So efficiency is one of the most frequently used terms in thermodynamics. Always we should consider this because it also will determine the cost for that system. Higher performance means higher of this input is converted to the desired output. You can see this equation for performance, and it indicates how well an energy conversion or transfer process is accomplished, like what you can see here. If we get more desired output from the required input, the performance or efficiency will be higher. Higher efficiency is desirable. And it is not only for thermodynamics, in other areas also we have that. Performance, higher efficiency or performance is always desirable. And the maximum performance will be 100%, which is something we don't have in real world, which all of the required input be converted to the desired output. Uh, so because of the some waste or a leakage or loss of uh, inputs, we cannot have 100% also desired output. So performance is usually less than one if we do this division, or less than 100%. Usually we uh, introduce the performance or efficiency in terms of percent. Multiply this by 100. And for example, you can see here for a water heater, the ratio of the energy which is delivered to the house by hot water to the energy supplies to the water heater. This is the efficiency of this water heater by doing this division for these two parameters, ratio of energy delivered to the house by hot water and the energy which is supplied for water heater, which can be electricity, gas, and other types of energy. We can calculate efficiency of this water heater. Higher efficiency means less fuel consumption to produce same amount of the energy. You can see here with different sources of energy how much is the efficiency of this typical water heater. Gas conventional, the efficiency will be 55%. With high efficiency, which with some modification, its efficiency will be 62. But with electric, the electric water heater can reach 90 or even 94% of efficiency. You can see how much is the differences between the efficiencies when you are using different type of the equipment. If you use the electric water heater, efficiency is much higher. So you can compare, when you select or you choose any equipment, you should think about its efficiency. More efficient means less energy consumption and less cost uh, for energy for that equipment. However, usually the equipment with higher efficiency are more expensive, but you should compare. This is an interesting example as well. You should compare when you pay for something, the initial price for the more efficient equipment is higher. But after a while, due to the less energy consumption, this higher price will compensate, and the uh, final price after 1 or 2 years includes the initial price for the equipment, or for example water heater, uh, plus the energy consumption during that 2 years should be calculated together to see which one is better option for your purpose. And also we have, the efficiency we usually show by this sign, we call that eta. Eta sub combustion means combustion efficiency. Combustion efficiency is for different fuels. When the combustion is a reaction, a chemical reaction, as you can see here, air and gasoline or any other kind or type of the fuels will react to each other, and the outcome of this chemical reaction will be these gases, these emissions, and also thermal energy. So we can define combustion efficiency of different fuels according to the amount of heat released during combustion divided by the heating value of the fuel burn. Heating value of the fuel burn means how much is the energy of a fuel if we burn it completely per kilogram. Simply, we have that definition for that. However, we have here a more specific definition for the heating value of the fuel. The amount of heat released when a unit amount of fuel at room temperature is completely burned and the combustion products are cooled to the room temperature. This is definition of heating value of the fuel. And this is the maximum energy which we can get from the fuel. Its unit, as you can see here, is in terms of kilojoule per kilogram. How much energy we can get from a unit of mass of that fuel, which is kilogram. So if all of this, if in our combustion reaction, for example, uh, we have this combustion reaction in the engine, if all of the energy is released, it will be heating value. I mean, the only in this exceptional condition, all of the energy is released. Then this combustion efficiency will be 1 or 100%. But usually we don't have that because of the, we don't have, we call these two as a reactants. Later in the future in applied thermodynamics especially, you will see more about the combustion and about the reactions, and we call them this all of these air and gasoline with these substances or materials as reactants. These reactants react and they produce products. We call these gases or this emission as products. If all of the energy is released by this combustion, we call that the complete combustion, and its efficiency is 1 or 100%. But usually we don't have that because we don't have enough reactants like air, we don't have enough air, we don't have that temperature which is required to release all of this heating value of the fuel. We don't have time. Imagine in the engine, combustion is in only in some millisecond. We need time to burn something completely. So the combustion efficiency is usually less than 100% and very lower than 100%, I can say. And as you can see here, when air and the combustion is reaction between different type of fuel and air, not air actually with oxygen, but because oxygen is uh, one of the gases in the air, we can call that air as well because air is reacted with that kind of fuel, but only the oxygen of the fuel is reacted with the of the air is reacted with the fuel. And as you can see, the products of this combustion reaction is are some emissions or gases like CO2, carbon dioxide, H2O, and which is water, and so on. This water, which is one of the product of this reaction, can be vapor or it can be liquid, which is product of the combustion. If you notice in the exhaust tailpipe, you can see, especially in the morning and in the cold area, you can see some vapor which coming out from the exhaust tailpipe. It is this because one of the products of the combustion is H2O or water. If this water is leaving, which is produced is in vapors phase, then these we have lower heating value. The energy which is released, we call that lower heating value. Then let me just repeat that. We have combustion reaction. Fuel and air are reacted as reactant in combustion chamber or any other places. Then products will, which are the emissions, will produce, and also energy will release. This energy which is released is called lower heating value if the water which is produced or H2O is in vapor phase. If this water is condensed and it is in liquid phase, this lower heating this energy which is released is higher heating value. Why we call, what is differences between them? Because as you can see here, when here initially the vapor is produced, but sometimes this vapor is condensed and heat of vaporization is also recovered by the system. So LHV and HHV, or lower heating value and higher heating value, will be different for a fuel in combustion reaction. The differences is only in the phase of the produced water from the combustion reaction, because it is effective on the amount of energy which we can get from the uh, combustion reaction. But usually the efficiency of space heating systems of residential and commercial building is usually expressed in terms of the annual fuel utilization efficiency, or AFUE, which accounts for the combustion efficiency as well as other losses such as heat losses to unheated areas and startup and cool down losses. So here you can see how the, you know, it is helpful, this information, to calculate how much is the energy to cool down or to usually to increase temperature of the building or residential or any kind of buildings by this information, because you know how much energy is released due to the combustion. It can be natural gas instead of gasoline. You know how much energy is released, but some of this energy is lost in the house. If we include also that losses of energy in our calculation, we can calculate annual fuel utilization efficiency of that building to for the required energy for that building. We have also other equipment which we may be interested about their efficiency. Any equipment or device which convert energy to another forms, we can calculate the efficiency or performance for that. Generator is a device that converts mechanical energy to electrical energy. You may know about that. So we can calculate also the generator efficiency, which is the ratio of the electrical power output. We get electric power output from electric power from that to the mechanical power input. The ratio of these two, we call them generator efficiency. The other type of efficiency, which may be useful for thermodynamics area, is thermal efficiency of a power plant. A power plant, as you may know, is a plant which provide electricity from different kind of fuel. So fuel is converted to the electricity. Then the ratio of the net electrical power output to the rate of fuel energy input for a power plant is the thermal efficiency of that power plant. And as I told you, in plants, we burn fuel, we produce thermal energy, then sometimes we produce the vapor, we heat, we have a boiling chamber, we increase the temperature of the water, for example. When its temperature is increased, it's will experience a phase change. This phase change it will produce vapor. Vapor will go to the turbine, and as you know, a turbine has a shaft and has a mm, blades and propeller. This vapor can turn that shaft or blades will come to the blade and push the blades. It will turn the shaft by rotating the shaft of the generator or turbine. The mechanical energy can be converted to the this rotation. This rotation will goes to the generator, and generator will mechanical energy will be converted to the electricity or electrical energy. Then overall efficiency of a power plant can be calculated or is the result of multiplication of uh, all of these three efficiencies. Efficiency of combustion, how much of fuel is converted or chemical energy of the fuel is converted to the thermal energy. How much of the thermal energy is converted to mechanical energy, and how much of the this mechanical energy is converted to the electrical energy. So we call this overall efficiency of a power plant. And you already know about combustion, thermal, and generator efficiency. Then total or overall efficiency of a power plant, a typical power plant can be calculated by this equation. W dot net electric or electrical power divided by higher heating value of the fuel which is used in that power plant and the mass flow rate of the fuel which is used in that power plant. Only by these three parameters, we can calculate the overall efficiency of a power plant. Which type of fuel is burning in that power plant, and how much is its higher heating value? How much is the mass flow rate, which is provided for the combustion in that power plant? And how much is the production of the electricity in that power plant? Simply by this equation, we can calculate the overall or net efficiency of a power. The other important performance which may be interesting for us is the performance of different type of lamps. The performance of different lamp is called or lighting efficacy. Is the amount of light output in lumens per uh, watt of electricity which is consumed by lamp. So the light is produced by using electricity. So the output is the light with this unit, and electricity is input with this unit. And as you can see here, the light which is provided by a 15 watt fluorescent lamp is equal to the light which is provided by 60 watt incandescent lamp. You can see how much the fluorescent lamp can be more efficient than the incandescent lamp. And you can see here the efficacy of different lighting system, type of lighting, combustion, like candle or kerosene lamp can provide and can be light source. You can see how much is their efficacy. Very low efficacy they can provide. How much is the candle? Just zero point 0.3, and you can see compared to the LED and other type of the light source, you can compare them which one is higher. The fluorescent lamp, you can see here how much is it, much higher than the combustion and much higher than incandescent lamps, you can see here. So because of that, it is recommended, and actually it is shifted from the incandescent lamps to the fluorescent lamp. And also we have seen the changes from the uh, these fluorescent lamp to LED lamp as well, because of their energy requirement. The energy requirement is very low, and they do not produce uh, temperature or thermal energy. You can see different sources of the light and their efficacy. And you can see the theoretical limit also is 300. It is according to the some calculation. But what is important here, you can see that according to different lamp structure, the efficacy is different. With same amount of electricity or electrical power, we can get more light by appropriate selection of the lamp. And also for the other equipment or appliances which you may use in the house, we can manage the energy consumption of the house. As you can see here, it is better to use energy efficient appliances which conserve energy. You can see here, as usual, to calculate the efficiency of any equipment, we need to calculate the energy which is utilized divided by energy which is supplied to that. For example, for this one is 3 kilowatt hour energy is utilized by this equipment for 5 kilowatt hour energy which is introduced to that. So the efficiency of this equipment is 0.6 or 60%. And you can see here how is it effective on the uh, the living cost or the house cost, the energy cost for the house. You can see here electric oven, convection oven, gas oven, frying pan, toaster, and so on. And you can see for different cooking temperature, cooking time, you can see how much energy is being used by this equipment. The highest one is for the electric oven, which consume 2 kilowatt uh, energy per hour. Then the cost of energy for this is 0.19 dollars or 90 cents, $19 the energy cost for electric oven. So we can choose between them which one is more efficient to be applied for the house. And also by this information which is provided in this table, you can calculate the energy consumption by different equipment, especially in the kitchen. The cost of the energy is important for us, but it is not the only reason which we should be careful, and we should select the more efficient equipment. As you may know about the combustion, as I told you, combustion is chemical reaction. Chemical reaction means two material, two substances, which I told you, air and fuel are reacted. Uh, then some emission and energy will produce. These emissions also are harmful for environment and also for human health, like carbon dioxide, which cause global warming, nitrogen oxide, and hydrocarbons, which cause smoke, and also they are harmful for human body. They can cause cancer. Carbon monoxide, which is toxic as well. Sulfur dioxide, which cause acid rain. You can see all of these gases are emission and are products of the combustion. And as you may know, the main source of the energy in many countries, and also we had in the slide before, is from the uh, fossil fuels. It's from combustion of gas, combustion of coal. All of them will produce these gases. Almost 90% of the energy which is provided for us, even the electricity, comes from these combustion-based energy. So it will produce these harmful emissions. What we can do is to consume less energy, to select more efficient material. Even we may need to pay more for them, but we can help to have a cleaner environment